Welcome back to Chem 4300. In this video, we're going to continue with Chapter 9 on electrodynamics. And now what we're going to do is we're going to look at other types of solutions to the electrodynamic wave equations and some of their properties. Now, one of the properties that we have to worry about for transverse waves moving in 3 dimensions is the wave's polarization. So what do we mean by that? Well, if you remember the wave solution that we got earlier, where it was a plane wave and we had transverse oscillations of the E field and the B field as the wave moved forward in space, those E field oscillations were oscillating along the x-axis in such a way that they were staying in a single plane as the wave moved forward. Similarly for the B, perpendicular to the E, the B's were oscillating in a plane that in that one plane as the wave moved forward. This is an example of what's called a linearly polarized wave, where the oscillations remain in a single plane. But that's not the only type of solution you can have. You can have other types of solutions. Remember, any kinds of linear combinations of solutions to your wave equation will also be solutions to your wave equation. So one type of solution you can have is what's called right circular polarized light. And in this solution, the E field will move counterclockwise in the xy plane as the wave propagates forward in space. And this is what that equation might look like. Similarly, you can have something called left circular polarized light, and in this case, the E field moves in a clockwise direction in the xy plane as the wave propagates forward in space. And the only difference between these two solutions here, as you can see, is just this sign difference here on the y component. Now, you'll realize that I've only showed you the E field, and of course in an electromagnetic wave there will always be a B field which will always be perpendicular to the E field at any point along the way, so I didn't bother to show those here just to simplify the picture. Now, most of the light that you deal with on a daily basis, the light that's coming from your light bulbs or from the sun, that light that comes at you is unpolarized light. So in other words, the light waves that are coming will have many waves that are coming at you with various polarizations. So there's no single plane polarized or circular polarized light that's coming at you in those cases. In fact, actually, those light waves that are coming at you have a range of frequencies and a range of phases, so it's generally somewhat what we would call incoherent light that's coming at you. But when light actually will interact with matter, then it's possible for light to interact with matter and for the light to be scattered away from the molecules that it's interacting with in such a way that the light can become partially or fully polarized. So for example, the sunlight that's coming in from, as light is coming from the sun, it's unpolarized light, has a range of frequencies, and when it hits a molecule, then it will get scattered in different directions. And depending on the angle of the scattering, you'll see that there can be partial polarization of the scattered light, or if it's perpendicular to the incident, then it can be plane polarized light. But if you looked at it directly on, then you would just see the unpolarized light that was coming from the sun, but it's at some angle that you see some kind of partial polarization. And you may have noticed this if you ever wear a Polaroid sunglasses and you're looking at a bright blue sky on a sunny day. You might look up and you see that as you tilt your head and looking through the glasses, that you'll see that there's some kind of light getting brighter or darker as you change the angle as you're looking at the sky. And that's because your Polaroid glasses are only sensing certain polarizations, and that partial polarization then will give you that sense that you're seeing light or dark depending on the angle there. Now, the equations that we looked at so far, we derived in the condition that light was moving in empty space. But as we just saw, light can interact with matter, and there will be consequences of that. And one of the consequences is that so far we saw that our dispersion relationship was linear, so that there was no dispersion of light. The speed of the light wave is independent of the wavelength as the light propagates through space, through empty space. But when we start having light propagating through dispersive media, so as it comes through the atmosphere or through glass or whatever, then we may find that this dispersion relationship is no longer true, and that there is some kind of nonlinear relationship that we have to learn about. So let's take a look at how you would get that relationship. Well, first of all, the derivation is relatively straightforward. You can simply just get the solution by replacing the electric constant and the magnetic constant of free space with the permittivity and permeability of whatever the medium that the light is traveling through. So when you do that, then what you find is that, unlike in the vacuum, you get a speed that's 1 over the square root of the product of those two constants, just like before, but now these constants will depend upon the wavelength of the light that's moving through. So the speed of light in that medium will be dependent upon the wavelength of the light. So in dielectrics, what you find is that the speed of light is reduced from the speed of light in a vacuum, so it's going to be some value that's less than 1, and that's going to be this ratio here, and generally that's expressed as 1 over the refractive index of the material. So this ratio of these constants, the product of the permittivity and the permeability over the electric and magnetic constants square root, is the refractive index of the medium. And what this also means then is that if you go back to the dispersion relationship, we saw before that it was just omega squared was k squared over the product of those two constants. Well, now that they depend on k, we now have a relationship that is no longer linear. So in other words, omega now has this functional form where this refractive index sort of destroys the linearity of the relationship, and this is what causes the dispersion. This is why you see rainbows and the speed of light changing as a function of wavelength. Okay. Actually, this is the parameter that's central to spectroscopy. Understanding why the refractive index varies as a function of wavelength is really what spectroscopy is all about.